So I'll do the introductions on our methodology that we used, and then Owen's actually going to do the practical aspects, because Owen done a lot of the heavy lifting with regards to the data analysis and what we've done. So I'm going to give, basically on the agenda, a sort of brief introduction onto why we're focusing on this area. So we're actually interested in embedded devices. It's not, large server farms, etc. We're actually considering embedded devices, and these are getting smaller and smaller and more critical information in them all the time. Then I'll give an introduction into side channel attacks, and that's going to be a history lesson as well, because we're going to go back a long way in time. And then we'll look at the tools and techniques that you can use for side channel data detection. Then we'll give an overview of our bare metal forensics project, which is the work that we're doing in conjunction with Edinburgh Napier University. Then I'll hand over to Owen, who's actually going to give a practical demonstration of the attack. So we've got a mixture of both background. Owen will cover the theory as well as the practical aspects of the attacks. So why are we interested? Well, we're interested in the evolving cyber threat landscape, and it's no longer about personal devices or, as I say, server farms, etc. The attack surface is now the 21st century city. Everything's wired in there, so the transport infrastructure, the power grids, your healthcare infrastructure, the financial infrastructure is all linked together. And these tend to be very small embedded devices that live out there for a long time. Connected cars are a very good example of that. So, if we go right to the very top, this was actually brought up for the Director of National Intelligence in the US. So we'd think of all the terrible things that are going on in the world. This is actually the biggest problem out there. And the ones that I'm picking out there is that devices are sent out nowadays. They're fielded with minimal security requirements and not much testing goes on either. And there's an ever-increasing complexity of how these things are connected together. So they're barely unknowable. And that's going to lead to vulnerabilities both in the fabric of society in terms of the infrastructure and in their case, the US government systems. So the hypothesis is that the current perimeter-based solutions aren't going to hack it. You can't just keep on bolting more and more security on, and how do you bolt on something that's a wearable chip anyway? You can't really say, we'll have a virus scanner running on that. It's just not practical. So how do you protect that all the way through? So who cares? Well, anybody that's involved in critical infrastructure protection is going to care rather a lot. If you're running a transport infrastructure, a financial infrastructure, a communication infrastructure, you're going to be really caring about that. If you're doing a supply chain, you're going to be really caring as well about vulnerabilities in your supply chain. There's already a massive problem in the industry in terms of counterfeit parts and how to identify them. Other people that care are threat intelligence centers. They need to understand what those threats are, distribute to them, and mitigate threats against that. On the other side of it, we've talked about how crypto can be used for both sides of it. There needs to be proportionate access in there for digital information where people are hiding in plain sight. So they have to gain access to those embedded devices if they're seized as part of a lawful investigation. And information assurance bodies are very concerned about it as well. And that's one of the good things about the industry. There's maturity starting to appear. Before, anybody could be a cybersecurity expert, and there's a lot of talk. Now there's some action. We're starting to see testable standards coming out in the industry. And just this week, the standards been released for cybersecurity for connected cars. There's standards there for payment card, for example. And we're also able to get cyber insurance as well. So all these embedded devices now need to be tested, and it's how do you quantify that, and what's the measurement science behind it to do it. So I'm not going to go into an advert for Keysight. Our job is to help those manufacturers of smart connected embedded devices bring them to market quickly. And we're involved in all sides of the life cycle. We're in there in design simulation, prototyping it, manufacturing devices or manufacturing test, and then optimizing things when they're in the field. So if you think about it, where is it easy to put in security? It's very much easier if you start very much on the left-hand side. It's very difficult to put the toothpaste in the tube after it's gone out there. And the costs in that are phenomenal as well to rectify problems. And once these devices are fielded, you probably never get them back, and you can't necessarily upgrade them. So what we're trying to do is to actually build in security from the outset, and also to educate engineers and the next generation of electronic engineers in how to design security in there. And that's why we collaborate with the security community, because the learnings and the science that we develop in conjunction with our academic partners, we can start putting it into tools, and then we can start much earlier in the life cycle to test for vulnerabilities. So, what do you need to protect endpoint devices for? That's a very old mobile phone, but you can still see the sort of sizes of the devices that are there. There's a number of ways into embedded devices. You can't embed a scanning agent on them. It's impossible to understand the supply chain for these custom system on a chip, because these chips are designed for very short production runs at very high volumes. So you don't actually know who manufactured them at any given time. There's no compliance regime in place. There's not many tests available yet. And very often there's minimal testing for market windows. So what we're trying to do is to exploit the industry interconnect standards to gain visibility into the device, because when you create an electronic device, you have to use a standard kit of parts and the standard communication protocols to build the device together. There's also manufacturing test ports put in there so you can build and program the devices, and we can use those to gain access into the device and have a look inside the device as well. And then lastly, we can use precision analog measurements to detect side channel leakage, so we can see if there's leakage inside the device. So when I say side channels, what sort of side channels exist? Well, there's a number of ways in. The first and probably the oldest one is electromagnetic emissions. Because the devices work at very high frequencies, there's electromagnetic radiation given off. You can check that radiation and look for correlation on the device itself. There's power side channel, which we're going to discuss at length in a presentation here. So as the device consumes electricity, if it's working harder, it's going to demand more current, less current, and there'll be a correlation between the operation of the device and how it consumes its power, and that might give you a clue into how it's working. You can also do debug ports attacks, so you can use things like JTAG ports, which are common attack ports. So these are the ports that are left on to program the device and test the device. In some cases, they're used to actually gain access to the device. And if you ever go to a mobile phone shop to have your device reprogrammed, that's the sort of test technique they'll use to get inside your mobile phone and unlock it. You can also do intentional electronic magnetic interference or jamming, or in some cases, you can create an electromagnetic pulse to put it into fault. And then you can do fault analysis and do some analysis on it beyond that. In some cases, you can extract the flash image itself, so there's usually test ports there. So you can take the chip off the device, read through the code, understand what it's doing, and then look for potential vulnerabilities and then go back and attack it later. There's over-the-air attacks as well, and network attacks. So very often there's a maintenance channel set up on a device, and you can use that to access it. And that can happen over the air, and it certainly happens over the air in phones. So for example, your phone, it can receive a firmware update, and there's a special channel where that comes through. And then lastly, you can actually read off the trace of the memory attack. And Google have already shown that with things like the Rowhammer attack, where you can put stuff in a memory location next to another memory location, in some cases flip bits. From our perspective, we do all this testing as part and parcel of that sort of design, optimization, and test process that we go through. So there's lots of bits and pieces in the catalog to actually look for these vulnerabilities. The channel is how do you orchestrate all that together to make sure that your device under test is secure. So let's talk a bit more about side channel, and this goes back a very long way. It actually goes back to World War II. And it was done in Bell Labs. And like all great discoveries, it was done accidentally. There was an encryption machine called SIGTOT that was used in World War II. And Bell Labs had the 131B2 mixer, snappily named, which was a piece of electronic equipment that actually put the encrypted data down the line. And what happened was that in the other part of the lab, they had an oscilloscope, and somebody else was running another experiment. Whenever this thing fired up, a pulse appeared on the oscilloscope. So they had an argument about who was causing it, and they realized that, you're breaking my experiment, what's going on? No, I'm not. And then sure enough, they discovered there was a correlation between, as this cipher machine was running, there's oscilloscopes pulsing on the other side. Now they were told they went back to the customer, who was the US Army, and say, well, look, this is a problem. And the Army says, no, it's not, there's a war on, don't worry. But being curious engineers, they ignored them and continued the work. And what they actually done was proven it. And that's what we're going to do today, is actually hopefully prove it as well. So they actually took the oscilloscope, put it on the other side of the street, 80 feet away, fired up the machine, and then lo and behold, they could read the pulses. It took them, they needed to do a trace for 1 hour, and then 4 hours later, they ran back across the street and said, here's your plain text, thank you very much. Now, based on that, they actually put a lot of countermeasures in the encryption machine, but it shows you how far back this goes. And this was only declassified 10 years ago, so it shows you how long it's going there. So, it's a very old technique, and that evolved into an electromagnetic technique called Tempest, where you could look at electronic magnetic interference as well. So I mentioned there was an oscilloscope, and that's the equipment that we're going to use today. The oscilloscope goes back a long way, 1934 actually, and originally it was an analog to analog device, so you would take in an analog signal and you get replayed on the cathode rays oscilloscope. At its time, you could buy 2 analog inputs at 10 megahertz for the princely sum of index adjusted £7,000 actually, and it had 52 valves in it. In a modern scope like the one you're seeing there, we can have up to 4 analog inputs running about 6 gigahertz. We have some scopes that run up to 63 gig. It's got 16-channel logic analyzer. It's got a waveform generator. It's got voice control. It's got a touch screen. And the signal processing runs about 20 gigasamples per second. So there's a custom ASIC in there. We can control it remotely, which Owen's going to do. And that starts at £940. So you're actually getting a lot more bang for your buck. So we're going to use the oscilloscope to do side channel collection and attraction. There's a number of different ways that you can get in, and these are some of the techniques that we use at the moment. You can use close field probes if you're losing for an electromagnetic signal, and these actually look for the electromagnetic field around the signal. Or you can use high-speed differential probes, and that's the technique we're going to use today, where you can actually get right in beside the components and jump on the component of interest, and then there's a low noise amplifier that sits right behind that. And the bandwidth of that is something like 2 gigahertz, so we can actually see very, very subtle signals in there. Beyond that, we put that into signal processing, and we use a number of techniques where we can decimate the signal, average the signal, and summate the signal as well. And then we can also put very accurate triggers in there so we can see the signal of interest. We can also run signal processing and like Fourier transforms. The rather interesting thing about this is that once we've got the signal, we can tweak it around a bit and then shoot it back out. So we can actually do full replay attacks as well. Now, in the back end of that, we can actually look at any interface we want to do. So this is the kind of, if you like, the nervous system of all modern devices. A CAN bus is the device that goes through your car. We can look at that bus and analyze it. PCI is an obvious standard you're aware of. USB, we can analyze that, jam that, get signals out there and look for side channel. And then we can look at debug ports like RS-232, JTAG, and then sensor buses like I2C. And then we can also look at RF signals and work in the frequency domain as well, and do gated samples and FFTs on that. Plus, the other good thing is we can take all that and run it in reverse, so we can detect a signal and push it back in. Of particular interest, and one of the ones that's most of interest to engineers nowadays, is an embedded device is going to have a battery in it, and battery life's critical. So there's huge amounts of engineering put into maintaining batteries, making them work, and getting the maximum efficiency. And as with a recent phone that went on fire, you can understand the importance of making sure that batteries work correctly and the cost of things when they don't. So there's lots of analysis software out there to do power analysis, and there's lots of special techniques as well. So it's a bit of an eye test, but you can see the 2 lines at the top are probably a low-cost probe with probably about 35 megahertz bandwidth, and you can see it's fairly indistinguishable. The one on the green line on the bottom, you can see some very systematic nicks on that, and that's because we're using a very high bandwidth sample and we've dropped the noise floor. So even though it looks like there's just a bit of ripple in the power supply. There's hidden signals inside there. And if you dig deep enough, you can start exploiting those signals. And you can see on the right-hand side, we can actually take that and go into the frequency domain and actually do an FFT on that, and then we can find the underlying signal that's running in there and find out how fast encryption is running, for example. So, overall, if we bring all those components together about signal processing, signal analysis, and signal collection, we can come up with what we term bare metal forensics. And this is the program we've been working on with Napier. So if you think about all the good mathematics that we've just heard from Bill, we can make it mathematically secure on the outside. It's a black box. We can design it to be as secure as possible. However, it can't run in a vacuum. There'll be electronic equipment that runs underneath that. There'll be a physical implementation of your cryptography which will be built using standard components. And then underneath that, there'll be absorbed phenomena. It has to consume power, it has to radiate emissions. You can't make it perfect. So there'll always be a bit of leakage in there. So what we can do is we can take over control of the device and stimulate the device, put it in the manufacturing mode or load code onto it. Then we can analyze the data that's going in there, and once we understand what it's doing, we can set up trigger points. So if we know once it's starting to do encryption, we can set up triggers in the device. And then we can start analyzing the electromagnetic channels and the power channels that go with that. And that's kind of where the demarcation between myself and Owen stops, because the interesting part's what happens beyond that. And it's notionally big data, complexity type stuff, which is very advanced signal processing in the back end of it. And if you analyze that raw data, you can start inferring how the device works, and then infer operation on the device itself. So with the project, we've kind of had this division of labor. So Keysight, we've done all the high-speed signal acquisition, capture, and generation. We've loaded the equipment to Napier University. We've provided the signal analysis and device measurement science, and also participated in the project as well. And then on the other side, we have Edinburgh Napier University, who are well known for world-class forensics research. You have an accredited MSCs in digital forensics, cryptography, and then you have all the partnerships with the public and private bodies in Edinburgh as well. So what sits in the middle of that is that we've partnered with Data Lab, who are designed to link up industry and academia and look for data science type problems that have to be solved. And we brought that to the table as data science problem. Because we have the data, the analysis is going to give us more insight into that. So Data Lab has kindly provided the linkage with the university and done the matchmaking. So it's a kind of three sides of the triangle, and it's been a very fruitful piece of research. So if we go back to the forensic analysis process, we need to collect the data, and I've shown how we can use high-frequency probes to do that. We need to extract the data, so we've got advanced signal processing inside the device that's doing some of that pre-processing. And then we can do some data processing in the back end of that. What remains now is how do you interpret that data, and how do you report out on that data on the operation? So with that, I'm going to hand over to our academic colleague, Dr. Owen Lowe, who's going to explain more about the theory behind the data analysis, and also hopefully give us a live demo of the work.
Thank you, Doug.
Thank you.
Okay, hello everyone. So before I begin my presentation, we're going to do something slightly unusual. Adrian, could you help me out here? So the idea here is that Adrian would like to ask you guys for 16 numbers from the range 0, 1, all the way up to 99. It's totally up to you what numbers you pick.
So as Owen said, we're going to generate the key. You are going to give Owen the key that he has to crack. Okay, and we'll see if it matches. So we need 16 pairs. Okay. It can be hex, but Owen said from 00 to 99. But it can be FF, that's allowable. So stick your hands up if you want to give me a number. Okay, 20?
16.
16?
1 second, 20.
Okay, that's going
16.
in. 16? Who's next? Stick your hand up. This is not a quiz that you need. Yeah? 54? 13?
You need to slow down, but I can't type this quickly. 37.
37, yep. 50.
50.
Yep. FA, the first hex.
Okay.
How many more do we need to go?
That's 1, 2, 3, 4, 5, 6, 7 we've got so far.
7, so we need at least twice that. So, yep. 7F. Okay. Next. 42. That's the meaning
So
of
I got
life.
BB and 42 there, yeah?
BB. Okay, for Bill Buchanan, that's a good one.
Yep.
That's always works. Yep. 16 again.
Good.
Okay. Okay, who's next? Is that, how many more do we
That's
need?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. so
11.
far.
So we need another 5. Yep, that's 5. 0E. 0 echo. Okay. 4 more. You at the back. Yes, you.
22.
22. Thank you very much. 3 more. You.
29.
29. Fantastic. Yep. A4. Fantastic. And who's the final one? You have your hand up. That's it. Yep. 5E.
5E, okay.
5 echo. I think that's 16.
Yep, that's 16 numbers, and let me just save this.
Okay, otherwise we'll have to go through that again. Is that Owen? Is you okay?
That's okay. So what I'm doing here right now, I'm just going to program this Arduino to use that code for AES encryption. I'm aware that I've not really gone into details there, but all should be clear very soon. So just give me a second whilst I upload that code with the key that you've provided me. Okay, we're good to go. So, hello everyone. In my segment of today's presentation, the last presentation of today, what I'm going to look at is a description, a research-focused description on the ideas behind side channel attacks. And in particular, I'm going to look at how we can potentially implement power analysis attacks on the AES-128 algorithm. Oh. Okay, as a quick introduction, my name is Owen Lowe. I am a research fellow at Edinburgh Napier University, and in the past I've worked in numerous areas of research, including digital forensics, health informatics, and digital identity. My current focus is on hardware security, and I am working, as Doug said, on the bare metals forensics project. So originally, I was going to give a quick bit of background on the ideas behind the bare metal forensic project, but Doug has already helped me with that, so I'm going to skip ahead straight away. Side channel attacks. So what exactly is a side channel attack then? In essence, a side channel attack is an attack on the information of a cryptographic device. The concept of information in the context of a side channel attack primarily relates to the secret key used in encryption and decryption functions. Now, for example, in AES, which is a symmetric key cryptography algorithm, basically, this means that the secret key can be used and is used for both encryption and decryption functions. So if an attacker was able to obtain this key, then they do potentially have the potential to unlock a lot of data which they were originally not allowed to view. A side channel attack itself is carried out by monitoring the physical outputs of a system. This is as opposed to more traditional attacks, which is focused on the software layer of security, looking at vulnerabilities or bugs in implementation. Some of the side channels that you may wish to monitor when performing a side channel attack may include the power consumption of a device, the heat emitted by a device, the time it takes for certain cryptographic operations to take place, and even the sound emitted by a device, if it has any capabilities of emitting sound. Within the scope of this presentation, as the title might imply, we are going to focus on the idea of performing side-channel attacks via the monitoring of power consumption. This idea of monitoring power consumption you'll find in literature is more formally known as power analysis. And the hypothesis in power analysis is that there is a correlation between the level of power consumption and cryptographic operations of the device under attack. To put it another way, power analysis aims to deduce the secret key of a cryptographic device by monitoring the power consumption of the device during cryptographic operations. What you also find in literature is that there are three primary categories of power analysis attacks. To name them, this includes simple power analysis, differential power analysis, and finally, correlation power analysis. And in the slides which follow, I'll briefly give an overview of each of these three forms of power analysis attacks. So firstly, what we have here is known as simple power analysis, SPA for short. The idea behind simple power analysis is to use visual interpretation to gather information about a cryptographic device. So what we see here in this figure that I've presented in this slide is a real-life example, actually, of a Arduino Uno as it is running AES-128 encryption. If you're familiar with the inner workings of AES-128, and I will come back to the details of how AES-128 works later on, what you will know, however, is that there are 10 main rounds of operation in AES-128. Focusing on that graph and focusing specifically on the nadirs, the lowest points in your data, you can easily tell that just from visual analytics alone, there are obviously 10 unique-looking nadirs, which relate back to the 10 rounds of operation in AES-128. And this type of simple power analysis attack we found also works in AES-192, where there is 12 rounds of operation, and also AES-256, where there are 14 rounds of operation. So you'll get 12 of these nadirs and 14 respectively for those two forms of AES. My point here is actually simple power analysis is very useful from a reconnaissance perspective. Suppose that you've got a black box device and you want to attack it. You know that it's running some sort of encryption, but you have no idea what type of encryption it's running. If you're able to get a power trace similar to this one, then you can easily tell that it potentially may be running AES-128, exploit that fact, and mount some more powerful attacks, which would allow you to deduce the full 16-byte key of AES-128. So one category of attack which is capable of deducing the full secret key of AES-128 is known as differential power analysis. In differential power analysis, the aim is to try and detect small variations in power traces based on the output of cryptographic operations. One of the primary examples of this was presented in a paper titled Introduction to Differential Power Analysis, where they noted that by monitoring the least significant bit of a cryptographic output, they found that depending on whether or not the LSB, the least significant bit, was 1 or a 0, it would, over a large enough sample of data, be slightly different. So in this example here, what we're seeing here is that when a cryptographic output produces a least significant bit of 0, given a large enough sample size, it consumes a bit more power in comparison with when the least significant bit is 1. And the fact is, it really doesn't matter which of the two consume more or less power, so long as the authors of this paper have demonstrated, they do have a variation. So the general idea behind mounting an attack using differential power analysis is to try and predict what the least significant bit of an output of a cryptographic device would be. And we would do this for each key guess. This would involve basically gathering a large number of power traces as the cryptographic device is running some sort of either encryption or decryption function, and then sorting your real-life power traces into two subsets of data. Subset 1 will consist of all power traces where you feel, based on your key guess, the least significant bit, let's say, is 1. And subset 2, where you think that based on your key guess, the cryptographic output would produce a least significant bit of 0. These two subsets of data are averaged independently. And finally, the idea is to subtract the two sets of data on a point-by-point basis. What you will get from that subtraction is simply a series of numbers. And that series of numbers will tell us whether or not there's any significant difference between your two subsets of data for each of your key guesses. If there is significant difference, then there's likelihood that your key guess is the correct one. Whereas, if there is no significant difference, the two traces should cancel each other out, meaning that your key guess is the incorrect one. Okay, and lastly, we have what is known as correlation power analysis. In correlation power analysis, we aim to correlate the actual power traces of a device against a hypothesized model for each of our key guesses. So from this example here, if we thought that one of our keys in AES-128 was a hex value 65, we would produce a power model of key 65, and it's assumed in this form of attack that every other key guess will have different characteristics in terms of its power profile. And what we would do is we would compare our hypothesized power model against our real-life power traces for each of the key guesses possible. So this would be the hex values in the range of 00 all the way up to FF. Naturally, the power model, the hypothesized power model, which most closely matches our actual power model, will be our correct key guess. Okay. In order to understand how an actual power analysis attack can take place on AES-128, I do need to go into a bit more detail on the inner workings of this algorithm. Within the scope of this presentation, I'm not going to give an entire lecture on every single component of AES-128. I'll focus specifically on the functions we are interested in. But the fact is, if you are interested in learning how AES-128 works or any of the other forms of encryption, you can easily find many pieces of literature online. So as I said before, within AES-128 specifically, there are 10 primary rounds of operation. With the exception of the last round, the operations themselves will consist of subbytes, shift rows, mixed columns, and add round key. During the last round of operations, the only functions that will be ran will include subbytes, shift rows, and add round key. Along with the 10 rounds of operations, we also have what is known as the initialization stage of encryption. This is basically, to put it into simple English, it's simply the start of encryption, and that will consist of only the add round key step right at the top there. The last thing I want to note here is that decryption is actually the same functions in AES-128. However, the functions themselves, the steps, are simply reversed. So, the attacks that we have implemented via power analysis will focus specifically on the add round key and also the subbyte steps of the first operation of AES-128. So that's the two functions I will describe within the scope of this presentation. Let's start with add round key. Add round key will occur during the initialization stage of AES-128. And basically, the algorithm itself will expect two sets of parameters. The first parameter is your plain text values, the values that you actually want to encrypt. And the second set of parameters is your cipher key, the secret key that you want to use for encryption and decryption functions. During the initialization stage, AES-128 will arrange your plaintext values and your cipher key values into two independent 4x4 matrix, as shown in this figure here. The actual function of add round key here is really quite simple, actually. All it's doing is an XOR between each plaintext value and key value. And this will occur on a one-to-one basis. So for example, plaintext value 0 will be XORed against key value 0. Plaintext value 1 will be XORed against key value 1. Plaintext value 2 will be XORed against key value 2, and so on and so forth. So we can easily express the add round key function in the equation P sub I XORed K sub I, where I is the value range from 0 to 15. After the add round key function has been computed or operated on, for each result in the add round key, the sub-byte step will substitute the value with a constant value from a lookup table. This lookup table is more formally known as Reindale's S-box, and hopefully I'm pronouncing his name right there. The sub-byte step itself can be represented in the equation where I've presented in the slide here, where S with the open and close brackets simply expresses a lookup on Reindale's S-box. And from the sub-byte step, much like add round key, there will be 16 outputs, one for each of your plaintext and key value pairs. To put that into a bit more context, here is the example of the Reindale S-box. And one thing I should note here, or emphasize, is that it's constant. It's been designed once, it's publicly available, and it never changes. And you might be wondering, what is the Reindale S-box? I don't think I described that. Well, in essence, the Reindale S-box is used to provide non-linearity in your encryption or decryption functions. It's been mathematically proven, don't ask me how exactly, but it's been peer-reviewed to ensure that basically things are mixed up a lot more during your encryption to ensure that it's not so easily cracked. The actual act of doing a Reindale S-box lookup is very simple. We start from a row and then move towards our columns. So if, for example, if we had the add round key result of A1, we would start in our row and work our way down to A1 and then move right towards the columns and find a matching one. And in that case, circled in red is the sub-bytes, which would replace our add round key result A1. Therefore, we'll end up with hex value 32. Okay, this brings me back to power analysis at this point. Having given an overview of the functions of AES-128 that we are interested in for this form of attack, let me describe the attack itself. In this form of attack, we have to assume that there are three variables. Two are known to the attacker, and the third variable is the variable we wish to solve. It's the unknown variable. The two variables we will have to have knowledge of in the scope of this attack will include the plaintext values and also Reindale's S-box constant values. Reindale's S-box constant values is, like I said before, publicly available, so that's not an issue for an attacker. But sometimes I must admit that plaintext values are a bit difficult potentially for the attacker to either observe or have capability of even knowing. So within the scope of this attack, we have to assume that the attacker does have the capability of feeding in new plaintext values to a cryptographic device, or otherwise it simply won't work. The third variable, naturally, is our 16-byte cipher key that we want to try and solve using power analysis. So I think the simplest way to describe how this attack works is that we first make a key guess, and this will be within the range, hex value range of 00 to FF. Then we calculate the sub-byte output based on the equation presented in the screen here. And finally, we compare the output to our real-life power traces. And we do this for each and every single key guess. And basically, the idea behind the attack is the sub-byte output which most closely matches the real-life power trace. And remember, the sub-byte output is derived from the key guess. The one that most closely matches will be the correct key. And we do this 16 times, and we have our full 16-byte AES-128 cipher key. One thing I should note is that although both differential power analysis and correlation power analysis can take advantage of this form of attack, the actual implementation itself will differ quite a bit. So in the next slide, let's have a look at how we can actually implement this attack using both DPA and CPA. For differential power analysis, what we want to do is gather a large number of power traces as the add-round key and sub-bytes function is running on a cryptographic device. Remember that within a differential power analysis attack, what we're really trying to do is detect any variation in power consumption based on the least significant bit of output, I should note. The least significant bit of output we want to try and determine, in this case, will be the sub-bytes output. So what we do is we apply a key guess, we calculate the sub-bytes output, and once again, remember we can do this because we know both the plain text values from that equation and also the Rindale S-box constant. And we sort our power traces into our two subsets of data based on that prediction. We do our averaging, and then we do our calculation on the difference between the two sets of data and log that result. And we do that 256 times for all possibilities in the hex range of 00 all the way up to FF. Naturally, the result with the highest significant difference will allow us to know what one of our correct keys in AES-128 is. And you can do this 16 times, and in theory, you should get your full 16-byte key. So that's differential power analysis. For correlation power analysis, as similar to DPA, we need to gather a large number of power traces as the add-round key and sub-bytes function of AES-128 is running. However, instead of trying to predict the least significant bit output of the sub-bytes step, what we want to do here is try and model the output of the sub-bytes step. So one of the simplest ways we found of modeling a power consumption trace is to simply use the Hamming weight algorithm. If you're not familiar with the Hamming weight algorithm, it's a nice simple algorithm which can be used to simply get you a count of how many bits are set to 1 in a binary output. So for example, with binary number 0011, our Hamming weight would be 2, whereas with binary number 0001, our Hamming weight would be 1, because 1 bit is set to 1. So once we produce a power model of all the possible sub-byte outputs, we can then compare them to our real-life power traces. And the act of actually comparing our hypothesized power model, and each of the power models is derived from a key guess, against our real-life power traces can be achieved using a very well-known and formally established statistical equation known as Pearson's correlation coefficient. The simplest way I could describe that is it's an equation which allows you to compare the linear correlation between two sets of data. And it can tell you whether or not there's any linear positive correlation or any linear negative correlation between your two sets of data. So to put everything into context, what I'm presenting here is a real-life example of attacking a single byte key of AES-128 using differential power analysis. What I've highlighted there in circle with that light blue aqua line is our correct key guess, which maps back to key value, hex value 65 in this example. And what you can tell there from that result is that clearly that key value, that key guess, has the most significant difference in comparison with all our incorrect keys. Similarly, in implementing correlation power analysis, this is the type of result you might expect to see. Once again, we're using key 65 as the example, and circled there is basically the correlation coefficient between our hypothesized model of key value 65 against the real-life power traces. What we're seeing here is a negative correlation between our real-life power traces and the hypothesized model. One thing I really should note here is that, in my opinion, CPA, correlation power analysis, seems to produce results which are a lot cleaner to interpret just from a visual analytics point of view. If you compare that result back with DPA, you can see that despite the other lines being the incorrect key guess, it is still highlighting some peaks and nadirs, and depending on how noisy your signals are, how cleanly you capture your signals, there is potential for a greater amount of false positives in differential power analysis. Okay. That's the theory over, which brings me back to the demonstration over here. Let me just make sure this is working correctly. And I'll plug in my laptop so you can see what I'm seeing on my screen. Oh. Great. And let me quickly just bring up the slides once more. So what you're actually looking at over here is a setup which contains a Arduino Uno. We've got our laptop and also the oscilloscope. Early on, we asked you guys to give us 60 numbers, which we used as the cipher key value in AES 128 operations. The Arduino itself has an implementation of the add round key and sub-byte step. And what happened when I started that data capturing about 18 minutes ago was that at periodic intervals, my laptop was sending a signal to the Arduino Uno to perform an encryption on some arbitrary plain text data based on the cipher key you gave us. Every time the Arduino Uno ran the add round key and sub-bytes function, what happened is that the oscilloscope will capture the power consumption of that device, and it will send that data, the actual power trace, back to my laptop. And this will occur iteratively. It has to occur quite a number of times because we need to get a large enough sample to get a correct key guess. So at this moment in time, I believe that the data capturing has been completed. And if I recall correctly, what I did was I saved my results into a folder called results. Let me just show you what the actual raw power traces look like. So this finished running at 16:42, 10 minutes ago. So this is one example of the raw power trace visualized as simply a line plot when the Arduino Uno is running the add round key and sub-bytes step. And to be honest with you, if you were to just perform visual analytics on each of these individual traces alone, you struggle to really make out much of a difference. So within the scope of this demo, what we've done is we've implemented correlation power analysis and also differential power analysis. DPA itself, like I said before, can produce a lot of false positives. So I'm going to focus specifically on giving you an example of hopefully breaking that encryption using the Hamming weight power model, which falls under the category of CPA. So let's just give that a second to run. And I should know at this point what's happening is within the software we've written itself, we are producing a set of hypothesized power models from each of our key guesses. And in the background, what's happening is comparing those models against each of our real-life power traces. Once it gets the result, it will plot it into a very nice-looking graph here, which was originally developed by Stephen Follick, one of our interns over there. And hopefully that's the correct key. So how do we know if it's the correct key or not? Luckily, I wrote it down, so let's have a look. So what I'll do is, yeah, okay. Yeah, look, that looks pretty much right to me. So our key guess is hex value is 2016, 54, 13, 37, 50, FE, yeah, 7F, BB, Bill Buchanan, yep, 42, 16, OE, 22, 29, A4, 5E, yeah. We've got 16, well, we've called them peaks here, really, they're nadirs, but we've got 16 nadirs here, which relate back to the 16-byte key of AES 128. What we're seeing here is that with each of these nadirs, because we're using the Hamming weight model and calculating the correlation coefficient, what these peaks are showing us is that there is negative correlation between a hypothesized model of, say, key number 20 against the real-life power trace, and key number 16 with the real-life power trace, and so on and so forth. Okay, so that's demonstration over, and just to give a final piece of information, this is an example, older example, using a different charting library, but this is an example of what the result may look like using differential power analysis. If we were to count the peaks there, you will find that there should be 16 peaks, but like I said before, the results here are nowhere near as clean as CPA, therefore there is potential for false positives. And finally, this is another example of correlation power analysis on a full 16-byte key of AES 128 using an older charting library, but if you count them, once again, there should be 16 nadirs, which relate back to the 16-byte cipher key of AES. And I think that's the end of my talk. Before I finish, within these PowerPoint slides themselves, I've got a list of references at the end of the slide. So if you want to learn more about this topic, feel free to read up on each of these papers. Thank you for listening.